So let's continue our discussion of the x86 processor architecture by taking a look at the x86 instruction set. So in this session, we'll look at the instruction categories that are available with the x86. We'll look at the instruction formats. And then lastly, we'll take a look at an example of some x86 assembly language code. And I'll go through each of the lines and to give you an explanation of what's happening within this piece of x86 assembly language code. First off, the instruction category. So the full x86 instruction set contains several hundred instructions. So there's lots of things that we can do. So let's look at some of the more important instructions common to user mode applications and then also to device drivers. So being able to, for example, create interrupts that allow us to access different input and output devices. First off, let's look at data movement. So the MOV command, or the MOV instruction, copies data values referenced to the location provided as the first operand. The CMOV CC instruction conditionally moves the second operand's data to the register provided as the first operand. So if the CC condition is true, whatever that condition may be. Next, we'll look at stack manipulation. So we can push and pop on the stack. So if we push, we decrement the stack pointer in ESP with the x86. Then it places the 32-bit operand into the stack location pointed to by the ESP. And then pop copies the 32-bit value pointed to by the ESP and increments it by 4, right? So if we push, it means we add something on top of the stack. And we decrement. If we pop, it means we're taking something off of the stack and we increment to where the top of that stack now is. Next, arithmetic and logic. So add and sub, pretty straightforward, performs integer addition and subtraction. Inc and dec, we can increment and decrement the operand by 1 as an example. And then we have some other math that we can perform. So multiplication and division, so mul and div for unsigned multiplication and division, and then imul and idiv for signed integer multiplication and division. So yeah, I just repeated that there. And then we have logic, right? So first we've seen the arithmetic, now we've seen the logic, and or XOR. So it performs logical operation on two operands and stores the result in this designated or the destination operand location. And then not, the difference between and or and XORs is they're using two operands. With not, we just use one. So the inversion operation on a single operand. So whatever that operand is, we reverse all the bits that are associated with that operand. Next, conversions. So we extend a smaller data size to a larger size. So CBW converts bytes to a word. So from the AL register to the AX register. Control flow conditionally or unconditionally transfers execution to an address. So for example, the jump, GMP, transfers control to the instruction at the address provided by the operand. Loop decrements the loop counter in the ECX, and if it's not 0, right, if we haven't finished the loop, it transfers control to the instruction at the address provided as the operand. So basically, if the counter is not 0, it means we're still in the loop and we still must go back to the top of that loop essentially and process that code again until we get to that loop counter being 0, and then we would move on past it. Next, string manipulation. So MOV moves the string element. CMPS compares elements at corresponding locations, and there's some other string manipulation instructions that we could do. These are just a couple of examples. Flag manipulation, right? We need to toggle flags accordingly depending on what the outcome is of an operation, for example. So we do that in the eFlags register. So STC, CLC, CMC, they set or clear or complement the carry flag. STD, CLD, STI, CLI sets, clears the direction flag and the interrupt flag. So S for set, C for clear, D for direction, I for interrupt. Hopefully that makes sense. Input-output, read or write data to or from peripheral devices. We use in or outs, depending on if it's input or output, of course. And we can move 1, 2, or 4 bytes between EAX, AX, AL, and the IO port, depending on the size of the data or instruction that's contained there. Then protected mode, access features of protected mode by using sysenter, sysexit, so we can transfer from ring 3 to ring 0 if need be. Syscall and sysreturn, or syscall and sysret, means we're going from ring 0 to ring 3. So it's the inverse of sysenter and sysexit. So individual x86 instructions are of variable length. It can range from 1 to 15 bytes as an example. And this variable length nature makes the process of instruction coding quite complex, and that's the idea of a CISC, right? A complex instruction set computer. So it is possible for a trailing subset of bytes within a lengthy instruction to perform a complete and valid instruction. And CISCs allow us to set things up in this way. And this is a notable difference from the more regular uniform instruction formats used in RISC architectures. And we'll see an example of this when we start talking about the RMAC architecture in a very short period of very soon here, that it's quite different in the way that we handle complex instruction sets. RISC computing, of course, we break things down into much simpler pieces, much smaller pieces. And lastly here, I just wanted to take a look at x86 assembly language. So assembly language can be used to develop programs of any level of complexity, of course, depending on your programming ability. Most modern applications are largely developed these days using high-level programming languages, but I'm, again, old enough to go back to when I did my computer science undergraduate degree. We actually had a course in assembly language. It's one of the tougher courses I took, but we were still coding in assembly language because the advantage of assembly languages is you can be really precise in the way that you code and maximize processor access and also memory usage for the size of that application. Assembly language code is much smaller, 8-bit for example, whereas the next level up, C coding, at 16-bit takes up much more space per instruction. So back then, when instruction processor access was at a premium, writing in assembly language was actually considered to be much more efficient, of course. So assembly language may still be used in highly specialized situations, like I'm mentioning here, where you want to perform extreme optimization. So maybe you have a particular processor on maybe an IoT device, on an Internet of Things device, and you want to maximize what can go on a particular small resource light device. So our code must ultimately execute its processor instructions, right? So if we start with very small instructions, then we can fit basically more instructions per finite space. All right, so let's take a look at an example of assembly language, and this is your classic hello world example. So I'm just going to go through some of the lines of this to give you an idea of how it all kind of fits together. So this x386 directive here, so our first line indicates the instructions in this file should be interpreted as applying to an 8386 architecture. So that's what this refers to, the 386. And also later generation processors. The second line, this directive specifies a 32-bit flat model and the use of C language function calling conventions. Okay. The next line specifies a stack size of 400, and the H means hex, right? So that equates to 1,024 bytes. Okay, so that's how big our stack is. The code directive indicates the start of executable code. And then these next 4 lines here are libraries. Okay, what are libraries? Hopefully you're learning about that in your programming language course. So we can reference system-provided libraries and the functions that are part of those libraries that we can then use in our code. And the advantage of that, of course, is reusability. We don't have to write the code ourselves. We can reference a library, like you would a library book that has a bunch of code that's already been created that will do the job that we want. to do. The public directive indicates that the function name main is an externally visible symbol. And then we get into our actual instructions. So this is our main code that actually executes here. And any line that started with a semicolon here is indicating that it's a comment. So this is describing the code that is to come. So we're saying we want to print the message. Okay, so this is our actual code. So we're pushing our message. So that's going onto the stack, and then we're calling a print function, which would be a part of one of these libraries. So extern printf, we can see here. And then the data directive indicates the start of data memory. So the message DB statement defines the message, which is the next line of code. Defines the message string as a sequence of bytes followed by a 0 byte. So here's our sequence of bytes. So hello computer architect or hello world. And it's followed by a 0 byte. And then the end directive indicates that we're at the end of the program. Okay, so this is just an example of a very simple assembly language example, piece of code that just basically prints out hello world or hello computer architect. Okay, so we can use this sort of programming structure, this syntax, in order to successfully write x86 assembly language. All right. So that's all I wanted to talk about in this session. So in this session, we've talked about the different instruction categories that are available for the x86 architecture, the different instruction formats. And then lastly, we've taken a look at a very, very simple assembly language piece of code and gone through the lines to explain what that piece of code actually does. Okay, all right, thanks for tuning in, and we'll see you folks in the next session.